Hi guys, welcome to the Principal Component Analysis lecture. We are in the unsupervised machine learning section. So in this lecture, we will talk about principal component analysis. As an unsupervised machine learning statistical procedure, PCA involves only a set of features. Let's create a simple scenario to learn the idea behind PCA. Suppose we have a dataset with P features and N observations. While exploring the data, it's very common practice to do scatter plotting. If we want two-dimensional scatter plots for a dataset with 10 features, we will have 45 scatter plots, and this number we can calculate using the formula given in blue color. What if we get more features in our data? Say we have 20, 100, or maybe even more than 100 features. So we will have lots of scatter plots then. So another very important question is, do you need all those scatter plots? Most likely, many of them may not be informative. So clearly, a better method is required to visualize such data sets of N observations when P is large. In particular, we would like to find a low-dimensional representation of the data that captures as much of the information as possible. For instance, if we can obtain a two-dimensional representation of the data that captures most of the information, then we can plot the observations in this low-dimensional feature space. So the PCA provides a tool to do this. PCA actually finds a low-dimensional representation of a dataset that contains as much as possible of the variation. The idea is that each of the N observations lives in p-dimensional space, but not all of these dimensions are equally interesting. So the PCA seeks a small number of dimensions that are as interesting as possible, where the concept of interesting is measured by the amount that the observations vary along each dimension. PCA uses an orthogonal transformation to convert a set of observations of possibly correlated variables into a set of values of linearly uncorrelated variables called principal components. If you recall a regression lecture, regression determines a line of best fit to a dataset, whereas principal component analysis determines several orthogonal lines of best fit to the dataset. So these orthogonal lines are perpendicular to each other in p-dimensional space. Let's explore with simple dataset having two features or dimensions x and y. Let's consider we have a dataset with two features or dimensions x1 and x2. So we have a black dotted line in the diagram, which is actually the regression line of the best fit to the data. This is first principal component, which is capturing the maximum variance in the data. So the PC1 determines, or the principal component 1 determines the direction of highest variability in the data. Larger the variability captured in first component, larger the information captured by the component. No other component can have variability higher than first principal component. So the first principal component results in a line which is closest to the data. That is, it minimizes the sum of squared distance between a data point and the line. So let's add another line, principal component 2, shown in color red. PC2 is perpendicular or orthogonal to PC1, and PC2 will capture the remaining variance in the dataset, and it is uncorrelated with PC1. So if the two components are uncorrelated, their direction is orthogonal to each other in the sample space, as shown in this figure, like PC1 and PC2 are at right angle to each other. Let's add another dimension, x3, as shown in the plot below. So for all subsequent principal components, the rule is same. They follow a similar concept, that is, they capture the remaining variation without being correlated with the previous components. So a couple of good things to remember in principal component analysis. Using principal component analysis technique on a dataset with large number of features, say P, we can compress the amount of explained features to just a few components. However, the challenging part for PCA is to interpret those components. The principal components are supplied with normalized version of original features. This is because the original features may have different scales. Imagine a dataset with features measuring units as gallon, kilometers, and light years. It is definite that the scale of variance in these variables will be large. Another important thing is performing principal component analysis on unnormalized features will lead to insanely large loadings for features with high variance. In turn, this will lead to dependence of a principal component on the feature with high variance, which is undesirable. So this is a very good example using principal component analysis. The 3D gene expression data, which are mainly located within 2D subspace, PCA is used to visualize these data by reducing the dimensionality of the data. So the three original variables, gene 1, 2, and 3, are reduced to lower number of two new variables termed as principal components, PC1 and PC2. On the left, using PCA, we can identify the two-dimensional plane that optimally describes the highest variance of the data. The two-dimensional subspace can then be rotated and presented as a two-dimensional component space on the right. So if you want to learn more about this example, you can follow the link on the slide. So guys, this was all about the principal component analysis. I hope you got the idea behind principal component analysis and how important this article and this PCA is when we have large number of features in our data. So the important thing is again to do some practice. Let's move on to the Jupyter Notebook to learn how to perform PCA using Scikit-learn in Python. See you in the next lecture. Good luck.